Thank you very much for the introduction. Also, thank you very much for inviting me to give a talk at this very nice workshop here. Today I present a kinetic model of the movement dynamics of colonies of Myxobacteria. This is part of work which I did during my PhD under the supervision of Christian Schmeiser at the University of Vienna. And I also want to mention my collaborators, Sabine Hittmeier from Uni Wien and Angelika Mannhardt, who is now at UCL. Okay, so here is just a very quick outline of my talk. First, I want to give you some biological motivation about what's the actual properties of this bacteria which we want to capture in a mathematical sense. Then I want to introduce how we did the modeling approach. Then also say something about the analysis of our model. And then, if time allows, I will talk about one possible model extension. Of course, there are like several ways to put more flavors into this model. Okay, then let's get started with Myxobacteria. So this is the main biological phenomenon which we are interested in. And these bacteria occur in the ground all over the world, and they are quite important for a healthy soil environment. They have an interesting life cycle, what you can see here on the right-hand side in this colorful picture. And during the life cycle, in the so-called vegetative growth phase, you can observe something called rippling behavior. So in this vegetative growth phase, these bacteria build huge swarms, and these huge swarms hunt and kill prey together. And during this, this is what you can, for example, see here in this microscopic image on the right-hand side, this gray one. These rippling waves, or sometimes also called accordion waves of Myxobacteria occur. And this is actually a video. I hope I can manage to show you. So rippling waves, because it's a bit complicated. Yes. No, the video is on the other side. Second, it comes, yes. Yes, so rippling waves, like as if you would put a stone into water, and then the water surface like does these rippling waves. So what are these? These are like bands of aligned bacteria moving like forwards and backwards, and eventually also like colliding. Biologists were interested in how this rippling behavior actually occurs. So what do individual bacteria do in order that this happens? Yeah, and so they did another experiment where they tracked single bacteria, so somehow they managed to color them, just to observe what they are actually doing on an individual-based setting. So here, this is also a video, which I'll hopefully show you in a second. But here, you can already see this again, bands of bacteria which are more or less aligned. Then they will move. And now I ask you to find your favorite red dot and see what it does during the video. Tube. Oh, and it's again here. Wait, I have to catch it. These two desktops, it's somehow a bit difficult. Yeah. So you see bands of aligned bacteria moving in one direction, and then now it should already have happened maybe several times. If a bacterium collides with one of its fellows, more or less frontally, it just reverses its direction. And the funny thing about it, and this is still a matter of investigation for biologists, is how they actually do it. Because these bacteria, they do not turn around, they just more or less stop and go in the other direction again. It's a very nice reversal behavior, which one can observe. Oops. And this seems to be crucial for this rippling wave behavior, what we saw. Okay, in general, this movement behavior of colonies of Myxobacteria are fascinating, like actually a perfect example for like a so-called emergence phenomenon. So you have like this individual-based rules of agents, and on the large scale, so basically if you zoom out and look at the whole swarm of bacteria, you see this large-scale behavior, which are the rippling waves. And in our case, the individual bacteria If they do not interact with any other bacteria, they just go on a straight run with approximately constant velocity. Here I underline constant velocity because, of course, this is a bit like a simplifying assumption, which I will address hopefully later in my talk. Then we got notice of this alignment tendency of bacteria, as well as the velocity reversals, which I just showed you. And another thing which biologists observed was that actually direct cell-cell contact is needed, that two bacteria can influence each other. So like really it's a local collision rule between two agents which leads to the change of their behavior. This is called C-signaling in a biological context. So this is what one can more or less observe on an individual-based setting, and then if you zoom out and look at the whole colony, you see this counter-propagating rippling waves. And this is what we wanted to model, and we chose the kinetic modeling approach. So this is actually a quite nice setting for putting this in the kinetic framework, meaning that we started by individual-based dynamics. So we have a huge swarm of n identical bacteria, some were moving on the flat substrate in R2. And then we describe each bacterium by its center of mass, xi, as well as by its velocity direction. So we assume that they all have the same speed as 0. It will be scaled away eventually, but they just alter in their direction of movement. Then we assume in the free flight phase, so if a bacterium doesn't interact with any other bacteria, it just goes on with regarding its velocity omega. So omega is just cosine sine of the angle, and the velocity angle doesn't change in this first model approach here. And then what happens if two bacteria collide? We assume that this collision happens instantaneously, meaning, so if you think, for example, of the gas dynamics in the setting of Boltzmann, it's a hard collision. So they collide, and immediately after they separate with their post-collisional states. So yeah, down here on the slide you can see like how a bacterium is described here. So like really a thin rod with its center of mass and moving in its direction. Okay. So then what happens actually if two bacteria collide? And here we wanted to model these two crucial behaviors, so like the alignment and the reversal. So we have two different collision rules depending on with which angle these bacteria collide. So if the angle is like less than pi/2, meaning that the bacteria more or less already go in the same direction, they just take the post-collisional states as the mean of the two pre-collisional ones. So like the mean of the two pre-collisional positions as well as velocity directions. That's a so-called like alignment or midpoint rule. And then the other thing is that these velocity reversals, which we could see, and so if bacteria collide more or less frontally, they just reverse the directions, the collision, the post-collisional space, state in space remains the same. Position is the word I was searching for, sorry. Yeah. Okay, so these are the collision rules. And out of this individual-based dynamics, we derived a kinetic equation of Boltzmann-type, which I will show you now. So we did this by formally performing the so-called Boltzmann grad limit. And yeah, we ended with this kinetic equation. Now the unknown function f is the distribution function of the states of a single part, as a bacterium, depending on its position x, on its direction phi, and of course on time t. On the left-hand side, what you see here is just a usual transport part. So this corresponds to the free flight phase of the bacteria if it doesn't collide. And on the right-hand side is the so-called collision operator. Local in position but non-local in velocity. It has two parts, of course corresponding to the two different collisions we are looking at. So the first part is the alignment part, the purple one, the second one corresponds to the reversal collisions. And then what I did not talk about yet is this factor B. It's the so-called collision kernel or collision cross-section. And it tells you how likely it is that a bacterium moving in direction phi star meets a bacterium moving in direction phi. And in our case, we consider two different B's, mostly. The first one is just the absolute value of sine phi minus phi star. This is, if you want it like this, the natural collision kernel. It comes really from the modeling, and it comes from the rod shape of a bacterium. You can see it as how much one rod sees of the other. So if you think of two vectors, it's basically the projection from one vector of the other, and it like tells how much bacterium sees of the other. And the other one, as we call it, Maxwellian mixes, if the collision cross-section is just equal to 1, mimicking the gas dynamics Maxwellian particles. Yeah, there. This we also consider. Okay, so now the first question which we are asking is like, okay, what do we do with this equation now? Do solutions exist, and also can we somehow like recover some sort of behavior, long-time behavior from the solution, which represents what we actually saw in the biological observations. So we started with existence, and existence of this whole equation is still an open problem. It's just to give you a hint why. It is structurally similar to the Boltzmann equation, where they handled the whole thing with like this randomized solution and worked a lot with a priori estimates from this logarithmic entropy, which we do not have due to the dissipativity of the alignment operator. So this does not really work here, and yeah, we are still thinking about it. So, but what we can say is something about the spatially homogeneous case of this equation, meaning that we assume bacteria spread equally in space, but just like alter in their direction of movement. And indeed, for this, yes, the analysis of this equation. Indeed, for this, we have an existence result. So, for any bounded collision kernel, remember the two collision kernels we are interested in are both bounded by 1. We have existence of a unique global solution in L1. So what are the main ingredients of the proof? Actually, quite simple, because the boundedness of the collision kernel plays an essential role, as well as mass conservation. So this I didn't say before, but of course the total mass of the bacteria is a conserved quantity. And with this, we were able to perform Lipschitz estimates on the collision operator, which then lead by a big argument to existence of a solution. So that we have mass conservation also means that the uniform equilibrium, so the uniform distribution is a stable, not stable, sorry, is an equilibrium of the system. And now the question is like, do we expect it to be stable, or do we expect some convergence to the uniform distribution? And of course the answer is completely not. This is exactly the opposite what we saw in the experiments, and also the opposite what the structure of the equation tells us. So because like the alignment has this concentrating effect of the angles, so a uniform distribution we expect it to be highly unstable. And indeed, this is true, because we have, in some assumptions, which I will explain in a second, exponential convergence to this equilibrium F infinity in the Wasserstein space 2. This equilibrium F infinity consists of the sum of two Dirac, centered at an equilibrium angle phi infinity, which is a conserved quantity under some assumptions, and exactly its opposite. So this is convergence to such an equilibrium is actually also what we expect, because having in mind our videos from before, we have like disaligned bacteria moving in one direction, meeting a wave of aligned bacteria moving exactly in the opposite direction, colliding, being repelled from each other, and so on and so forth. So this is actually what we expect. Yeah. And convergence to this we could prove under the following assumption, that we already assume initially that, so just to the assumptions when we have convergence to this equilibrium, we have to assume that initially the bacteria already grouped in two parts, like one group of bacteria moving more or less upwards with an angle between pi over 4 and 3 pi over 4, and the other group moving like exactly in the opposite direction with an angle minus pi over 4 and minus 3 pi over 4. So we have to assume initially that we already like have two groups of bacteria and no angles in between. So this assumption is necessary, because under this assumption we can determine the equilibrium now explicitly, because otherwise we would lack of a third conserved quantity. And in that case, the masses of each of the groups are conserved, as well as the average, so the mean angle, which is the average of both groups of bacteria. So this is necessary. And now, just some essentials of the proof. We defined the following Lyapunov functional with which we could conclude exponential decay and with which we could also control the Wasserstein distance. This is why we are in the Wasserstein space here. And not surprisingly, also this Lyapunov functional has two parts, one corresponding to one basically capturing the effect of the alignment and one capturing the effect of the reversal. So the blue part corresponds to the alignment collision, and it measures the variance in each group from the mean angle in each group. So these phi bar plus and phi bar minus are the mean angles in each group, but they are time dependent. So we expect them to change until they reach the equilibrium angle phi infinity, which is ensured in the reversal part of this Lyapunov functional, the purple part. And it just measures the quadratic distance from the mean angle in each group to the equilibrium angle. So yeah, indeed, when we look at the time derivative of this H, we find it decays exponential decay, and yeah, the control we need. Okay, this will be a bit clearer, I think, in the simulations to this. So I think the clearest thing here is this color plot on the left-hand side. So we started with initial conditions in tiny intervals, not opposite from each other. So we did not start symmetrically. And then what you see immediately, due to the reversal effect, that you have mass exactly opposite from where you start. And then after the alignment kicks in, so to say, and starts with this concentrating towards the two direct deltas, which are here at pi over 2 and minus pi over 2. So pi over 2 here is the equilibrium angle. And also quite interesting is these red lines which I drew here. These are the mean angles in the group. And of course, at the beginning, the mean angle is like concentrated where the mass is concentrated, but then you can see exponential convergence actually to the equilibrium angle. So this corresponds to the second part, to the purple part of the Lyapunov functional I showed you before. Yeah. Exactly. So this is basically all which I wanted to tell you to the first basic model. Yeah, summaries of results which can be found in this article. And now I quickly want to talk about one possible model extension of this. Depending on how much time I have, sorry, because of this inconvenience, I'm not really sure of, but I will just quickly say something about it. So we considered also the model with additional directional diffusion. Meaning if we go back to the individual-based dynamics, we still have that a bacterium in its free flight phase, the position changes towards its velocity, but now the velocity is not constant, but the bacterium like pivots a bit around. So we added this Brownian forcing term with intensity mu. So mu is then the diffusion constant, and on a kinetic level, the equation looks like this. So it's the same equation as before, but just with this directional diffusion term here in green. Okay. Now we try to do some analysis for this equation, and the presence of this diffusion puts it into some other functional analytical setting. So we also studied existence and stability of equilibria here. So of course the uniform distribution is still in equilibrium to this equation, so there nothing changed. But now the question is, do we really expect it still to be unstable? Because one can think if the diffusion is strong enough, then actually the uniform distribution becomes stable. And indeed, this is what happens, and this is somehow like a bit summarized here, hidden in this points of results. So we could prove existence of a global mild solution, this time in a L2 setting, because of this regularizing effect of the diffusion. But only if mu over m is large enough. So mu, as I said, is the intensity of the diffusion, and m is the total mass of the system. So which means there has to be enough diffusion to overcome this singularizing effect of the collisions, so of the alignment collisions specifically here. Under this assumption, we can prove this existence result, which goes hand in hand actually with a stability result of the uniform equilibrium. The main ingredients of the proof is actually proving spectral stability of the uniform equilibrium. This we did with an L2 hyperaggressivity method, where I won't go into any details. It's based on a method by Bomoho and Schmeiser. And with this L2 hyperaggressivity, so basically we have spectral stability of the uniform equilibrium, we were able to go to higher regularity in order to control then the nonlinearity of the collision operator, with which we then could conclude nonlinear stability of the uniform equilibrium. And then with a BK argument, also existence again. So this only works if this diffusion is strong enough compared to the collision. So, here, during this analysis, we did not find a concrete value of when does the uniform equilibrium become stable or unstable. So this is why we performed like a formal bifurcation analysis. And we found out, so we again investigated linear stability of the uniform equilibrium. And we found out that there exists a concrete value mu star if the mu is below so actually the important thing is this fraction mu over m. But of course we did this bifurcation analysis with mu as a bifurcation parameter. So if the diffusion is lower, is higher than this mu star, so strong enough, then the uniform equilibrium is stable. And if not, it becomes linearly unstable. So going to higher order in this bifurcation analysis, and also like inspired by the symmetry, so the flip symmetry and the rotational symmetry of our equation, we found that there is a supercritical pitchfork bifurcation, and actually two branches of solutions equilibrium solutions occur which are non-uniform, which are symmetric, and having in mind also this smeared out direct deltas a bit, because like in the no diffusion we had like these two direct deltas, and now we have this smeared out direct deltas. So yeah, these were basically just the main overview over this problem without going that much into detail. That was a formal bifurcation analysis, and I want to conclude actually with just two simulations. Here on the left-hand side, in the regime where the diffusion is not strong enough. So red are the initial data. It's the uniform distribution just perturbed at a little point, and you can see actually the two, let's say, regularized direct deltas occur, which occur due to the collisions, to the disalignment collisions, and they are symmetric and directly opposite from each other due to the reversal collisions. And then if the diffusion is large enough, here we started with like some random initial conditions in red, and then you can see convergence to the uniform equilibrium. Okay, and yeah, with this, the last part was just, of course, like giving an idea what a possible model extension could look like. And with this, I want to conclude, and thank you for your attention, and I'm happy to take it.
Thanks, Laura, for the nice talk. I was wondering if you could say some words about how you went from how you got the kinetic model.
At the limit.
Yeah, the limit. So how do you get the collision operator of that form?
It's actually, may I refer to your talk? So we started thinking of having in mind always like the Boltzmann setting, so to say, because it's quite similar. So the state space of the before the limit, so with the n particles, is the Swiss cheese you were referring to, and the collision comes from boundary terms of the collision operator comes from boundary terms of this Swiss cheese. And our Swiss cheese is not like something with holes, if you think of it, but something more like when do bacteria collide? So when do two rods touch each other? Which was described by, so each bacterium then was described by like a how to say, two-parameter, like a vector with two parameters touching each other. And there you have like your rules when it's allowed, so when they touch each other or not, and this we implemented in the in the boundary terms. It was quite messy, but yeah.
But then you get like in Boltzmann,
so yeah.
Sort of diluteness assumption, you get propagation.
Yeah, exactly. So then we get like this this equation with the two-particle probability density. So of course, this what I just referred to. We wrote down the probability density of the whole state system. Then we took the first marginal. Sorry. Not again. Oh, it's anyways, and then the equation was then depending on, so the collision operator had something with the two-particle density. Then we performed the limit. We used the molecular chaos assumption, for obtaining this equation. Exactly.
Thank you for your nice talk, Laura. It's just a question again on the modeling. What the timescales of these things and what allows you to not look at proliferation at all?
What do you, sorry, I think I did not really understand.
What timescales do you have your phenomena? So is that what allows you, is it that it's very fast to compare to the proliferation times of these bacteria, or is there other reason why you can not consider that they can proliferate? Because bacteria in soil, that's the type of thing that you expect to proliferate a lot, right?
So the data, what we had, also the data, like the observations, this video which I showed you, are actually all done in vitro. So we do not know exactly how they behave in the soil really. And of course, there I have to mention there are quite some similar simplifying assumptions involved there. To give a start. So this is. With these assumptions, we could recover some the basic things we saw in the experiments. But this is, I think, it doesn't give us validation of having that this is exactly the best way to model this. This is a way to write a reasonable mathematical model which recovers this movement behavior which we wanted to observe. But yeah, there is no deeper thing in it, I have to say.
Okay. Do you know what's the time length of one of these run phases? What's the time duration of a run phase or an average for this system?
This, I have to admit, this is something data which I could ask quickly, but I do not know now. So,
okay.
yeah.
Okay, thank you.
So.